So we've figured out how to simplify the heat equation, and we figured out how to use those simplifications to try to understand systems, right, in a practical sense. And so what I thought that we can do now is to basically take a look at what the simplifications that the heat equation undergoes whenever we have, the four classic sort of simplifying assumptions that we've talked about previously. The idea that, heat transfer is occurring in steady state, that material properties are constant, that there's no volumetric thermal energy generation, and that heat transfer is happening in one dimension. Whenever we have those four assumptions together, the heat equation simplifies drastically into something that we can solve using just like standard ordinary calculus. No need to worry about partial differential equations or anything like that. And so now let's try to take a look at what solutions to the heat equation look like, in the sense of like, what does the temperature distribution of an object look like in planar and cylindrical geometries whenever those assumptions are satisfied. All right, so we're just going to take a broad general look at it, and then we're going to try to study to see if we can't find anything that is, I guess, maybe intuitive and obvious and just confirm our intuition, but then also maybe find stuff that is unintuitive and not necessarily something that we would get from common sense, right? So we've already done plenty of planar cases before, but let's take a look at them again just in case. So just as a reminder of what we are considering by simple conduction, right? So like we would have something like a wall, all right? And we can assume that heat transfer is happening either from left to right or right to left. We define some direction x over which the heat transfer takes place, and that is going to be the only direction over which the heat transfer takes place, all right? So we don't really care about this heat situation whenever there's like heat transfer in any other direction other than left to right, all right? So obviously, we can have a scenario where the heat transfer is actually happening up or down, but it would only happen in one direction, all right, in order for the following analysis to work. We are also going to assume that there's no thermal energy generation inside of this material, right? This is just a nice normal wall. We are also going to assume that the heat transfer is occurring in steady state. So there might be some thermal energy that's flowing through the wall, but it's happening in such a way that the temperatures and everything else that are, properties of this wall or properties of the system that includes the wall, all of those things don't change over time. Okay? And then last but not least is that those material properties are constant. All right? So the thermal conductivity, the specific heat capacity, the density, everything about this material that is a material property is constant. It doesn't change in space, it doesn't change in time, it doesn't change with temperature or anything like that. All right, so these are the four assumptions. If we do that, we will wind up observing that the heat equation actually simplifies down into a very simple second-order differential equation. Perhaps the simplest second-order differential equation, which is just this. All right, that the second derivative of the temperature field with respect to x is 0. So whatever the shape of the temperature profile of this wall is, we know that it has to be a line because the second derivative of the temperature field is 0, which means that the temperature profile is linear. So in planar systems, whenever we make the four assumptions that we talked about before, or whenever those assumptions are true, we see that this has to be true and that by extension, the temperature profile inside of the system has to be linear. Now, let's suppose that this wall had a cross-sectional area AS, and that either side of this wall had temperatures T1 and T2. We can also say that the wall has some thermal conductivity T, and we can say that it has some length, or thickness L, all right? So how do these properties factor into this analysis? Notice that the K doesn't really show up when it comes to calculating the temperature distribution because of the fact that under the assumptions that we made before, the K actually doesn't matter. That doesn't necessarily mean that this temperature distribution can't be a function of K. It's just not going to show up by default in the actual differential equation. So what is the general solution to this differential equation? Well, we had seen it before. This is just a line, and that line has the following form. The temperature is a function of x. It's just C1x plus C2, where C1 and C2 are these undetermined parameters that are a function of what the state of the system is. And these things can be a function of, well, whatever piece of information you're given. So right now we have T1 and T2, but you might also have a situation where maybe you don't know the temperature, but you do know what the heat flux or the heat transfer rate on one side of the wall is. And then that will give you information about what these coefficients are. So operating from the perspective that we know the temperatures, so let's just try to figure that out. The way that you would normally solve for C1 and C2 is by applying boundary conditions, all right? So we say, if we assume that the x coordinate starts here, we would immediately figure out that by applying this specific value of x to this equation, this would just be C1 times 0 plus C2. And so, of course, the C1 is going to go away. And then this has to be equal to T1. So because this is equal to T1, we find that C2 has to be equal to T1. So wonderful, right? That tells us what this is. Now we can ask ourselves, okay, how do we find C1? Now, what we can do is replace the boundary condition that we used on the left side with a boundary condition on the right side. All right, so we can say that at x equals L, right, on the right side of this wall, C1 times L plus, and then I'm just going to write the T1 because we already know that that's T1. This has to be equal to T2. And so this gives us enough information to figure out what C1 is, as long as we know what these properties are. And so ultimately, we wind up obtaining, that C1 is just equal to T2 minus T1 divided by L. All right, and so when we actually plug this in, we will obtain the following general expression for the temperature profile inside of a planar wall when all the assumptions that we've made are satisfied. All right, so this is the expression. Now notice that the sign associated with this is going to be positive or negative depending on whether or not T2 is larger than T1. Right, this is effectively telling us what the slope of this line is going to be. So this is fully general for any two temperatures, T1 and T2. So this is the expression for the temperature. We've confirmed that it's always in line. But one thing that we should take a look at is to ask ourselves, what is the heat transfer rate through this wall? Right? What is the Q? So what is Q? Right? And can we get Q out of this information? And the answer is yes. So this is a planar system. We've made a lot of simplifying assumptions. One other thing that we're always going to assume is that whatever this heat transfer rate is, right, and we know that it has to be either left or right, we're going to assume that it's uniform in the sense that the heat fluxes at every point on this wall are going to be the same as long as I am not moving around in X, all right? So what I mean by that is that if I take, a little slice of this wall, so I cut the wall and I have this little cross section of the wall, the heat fluxes this way or that way at every point on that little cross section are going to be the same, all right? And it's actually going to wind up being true that the heat fluxes everywhere are going to be the same, but we don't know that yet. Let's show that that's going to be the case. So the reason that we have to make this little cut assumption is because we want to be able to write the heat transfer rate as the product of the heat flux times the cross-sectional surface area, all right? Now we're going to take an arbitrary cut. It actually doesn't necessarily matter where the cut is, right? So we can just assume that it's here. We'll show that it won't matter. So let's, for the moment, just assume that we are at this random value of x, that the heat transfer rate through this little cross-sectional piece of the wall is equal to some, heat flux that is the same everywhere in that cross-section times that cross-sectional area. So what is Q double prime? Well, remember that this Q double prime is better and more concisely written as Q double prime x, right? We're trying to ask ourselves, what is the heat flux that's happening in the x direction? And the reason that we want to do this is because we want to use the equation that we've written down for modeling heat transfer within objects, the equation that we use for conduction all the time. And that equation, or for at least the x component of the heat transfer, is just negative k times dt dx as. Now here's an interesting one, right? Because now this dt dx is a mathematical expression that we can directly plug in from over here. So this is a line. Finding dt dx is relatively simple. So all that we have to do is just take the derivative of this, right? So this constant goes away, and all we're left with is this expression right here. And so we can just rewrite this as T2 minus T1 over L times AS. All right. And so there's a couple of interesting things to note about this particular expression, all right, for Q. Now remember that this is an expression for full-blown Q. One of the things which is really interesting about this is that it's proportional to a temperature difference. Now the negative over here doesn't actually tell us that much meaningful information because remember, we don't know whether T2 minus T1 is negative or not. Like that depends on the setup of the problem. But we do know that whatever's happening, whenever I have a planar wall, the heat transfer rate that's happening through the wall is going to be proportional to this temperature difference. That's going to matter. We're going to see why that's an important piece of information in a second. The other thing that we can observe as a result of this particular setup is that notice that the heat transfer rate is proportional to a surface area. All right, so the bigger I make the cross-section of this wall, the larger the heat transfer rate is going to be. Maybe not that unintuitive, but this is also a piece of information that's going to matter a lot, okay? And last but not least, the heat transfer rate is inversely proportional to the length, all right? So the longer I make the wall, the less the heat transfer rate is going to be, all right? So although we'll talk about this in more detail later, notice, right, that we can already get some intuition for how we want to maximize or minimize heat transfer inside of planar systems, right, given some fixed temperature. So if you keep the temperatures fixed, if you want to maximize heat transfer, you want to make sure that you make L very small and A very big. If you want to minimize heat transfer, you make A very small and you make L very big, all right? So that's some important pieces of information. And then also, right, that the heat transfer rate is proportional to the temperature difference. Last but not least, notice, right, that Q double prime is just a constant, right? So minus K times this, all right? And that what that really tells you is that this expression over here is not a function of X, all right? So the heat flux not only doesn't change by assumption over any region in this cross-section, but it also doesn't change depending on whatever value of X you're doing your analysis in. So it doesn't matter that I cut my section here or here, I'm still going to get the same value of the heat flux. And so ultimately heat flux is conserved, so to speak, in planar systems where all of these assumptions are valid. All right? So this is the story for planar systems. Now let's talk about cylindrical systems where things get a little bit more complicated. We're going to see, like we talked about before, that there's a couple of things which are going to look the same, like certain dependencies that are going to look roughly the same, but that we're also going to see that there's certain dependencies which are not at all similar to what we saw before. So in a cylindrical system where we apply the same assumptions, right, we are once again left with this equation, and then of course we can get rid of the k. And so now this is my expression. Before, this simplified down in one dimension, in one planar dimension, this simplified down to a simple ordinary differential equation. This will simplify to a nice ordinary differential equation too, but it's going to be a little bit more complex than the one that we saw before. In cylindrical coordinates, and I suppose assuming that all of the heat transfer is happening radially, right? So you can imagine that we have a cylinder and all of the heat transfer is happening radially outwards, but it's not happening into or out of the board, right? It's not happening actually, and there's no like swirl, there's no movement of heat transfer, swirling around the cylinder. If we make these assumptions, then we can write down what the differential equation for the temperature profile as a function of R is going to be. And that's the following. Oh, pardon me. There we go. Just making sure that it looks as clean as possible. There we are. All right. And so you can see that basically what we've done is that we now have this R that's multiplying dt dr, and then we have this 1 over R outside of the second derivative operation. So how do we solve this? How do we find a solution for what the temperature looks like inside of a cylinder or inside of a cylindrical section? Well, this R actually doesn't matter because I can just multiply both sides of this equation by R and then everything goes away, right? So, gone. Great. So now we have to integrate this expression, and that's relatively simple, right? So if we integrate this derivative of R with respect to R, we're just going to get the same thing back. And if we integrate 0 with respect to R, what are we going to get? Just a constant. So we wind up observing that R dt over dr is equal to C1. Or, moving the R around, we get that dt dr is just equal to C1 over R. This is also straightforwardly integratable, right? This is just 1 over R, so using basic calculus rules, what we will wind up observing is that the temperature distribution of a cylinder or a cylindrical section is going to be the contribution, or the sum of the contribution of two terms. A logarithmic term, which is coming from the integral of the 1 over R, and then a constant, just like in the planar sense. So we still have a constant that I guess is maybe expected, but now the temperature profile is always going to be logarithmic, okay? So this is kind of the key change of what happens in cylindrical systems, okay? So how do we find the temperature distribution? Well, just like before, we apply boundary conditions to try to figure out, what these constants C1 and C2 are. But you're going to notice that this is actually a little bit trickier than in the planar case. How? Well, let's do a very quick, simple example. Let's suppose that I have a cylindrical shell, all right? So I have this cylindrical shell, and I'm going to say that the temperature of this inner, section of this shell is T1, that the temperature of this outer, part of the shell is T2, all right? So how do I find the temperature distribution given these pieces of information? Well, we can also write, if we want to, we can say, well, we have, some K, all right? This cylindrical shell has some thermal conductivity K. We can also say that this inner section has an inner radius of R1, and that this outer section has an outer radius R2. And then we can also say, this is a cylinder, right? We're simplifying it down because heat transfer is only happening radially, so who cares about the axial direction? But we can nevertheless say that the cylinder has some length L, all right? So if we do this, what is the temperature profile? Well, it's the same exact idea as what we had before. We're just going to substitute in boundary conditions, things that we know about what the temperature looks like on the inner and outer shell to get what the values of these constants are. And you're going to see that that's actually not going to be super helpful, but it will be interesting when it comes to deriving what the heat transfer rate looks like. So how do we do this? Well, in the first case, my temperature profile generally looks like this. So at R1, this is just C1 ln of R1 plus C2. We know that this has to be equal to T1. All right? This doesn't give me enough information to be able to solve for one of these constants, right? Because before in the planar case, this little term would have gone to 0, and so we would have been able to find C2. We can't do that here. We have to use the other boundary condition, which is that the temperature at R2 is equal to C1 logarithm of R2 plus C2 being equal to T2. So this is the expression that I get, all right? Now, how can we use these two expressions to try to find what the value of one of these constants is? Well, notice that we can manipulate these equations in such a way where I can take the first equation, like both sides of the first equation, and then subtract both sides of the second equation from them, okay? So what I'm going to do is I'm going to take this minus this minus this, and then generate a new equation. And the reason that I want to do that is because it's going to get rid of my C2s, all right? So if I do this, I wind up getting C1 times the logarithm of R1 minus the logarithm of R2. These two things cancel, right? C2 minus C2, that goes away. And then this is equal to T1 minus T2. All right. So this works out just fine. Now I guess the question is, how do we calculate C2, right? So we know what C1 is. Let me write it down over here. So let me solve this equation for C1. And the expression that we're going to get is not necessarily super complex, but it's still much more complicated than the planar case. Using logarithmic rules, right, this is the logarithm of R1 minus the logarithm of R2. That simplifies, right, using logarithm rules. And so we can write this C1 down as T1 minus T2 divided by the logarithm of R1 over R2. Okay, so that's what C1 is. How do we find C2? Well, we now know what C1 is. We would just have to insert it into this equation and then plug in the value of any of the other equations, right? So we can either analyze the system at R1, say that this is equal to T1, like in the equation we derived before, and then get that, but we could also just as easily do it for R2. So let's do it for R1, just so that you know what I'm talking about. T at R1 has to be equal to T1 minus T2 divided by the logarithm of R1 over R2 times the logarithm of R1 plus C2, and then this has to all be equal to T1. And so you can see how we can take this equation and then solve for T1, right? And so T1, or pardon me, not solve for T1, solve for C2. So we can solve for C2 by just saying, well, C2 is now equal to T1 minus this mess, right? Because all I'm doing is just moving terms around in the equation. And so we know R1 and R2, we know the temperatures, and so voila, we have an answer for what C1 and C2 are. So it's a very unwieldy expression in the sense that we've got these logarithms floating around, but it's what it is. This is the term that's going to be the most useful, though, because I want to show you something very interesting, which is, what is the Q? So if I take a little cross-section of this cylinder anywhere on the inside, I have to ask myself, well, what is the heat transfer rate that's happening through that little chunk of cylinder, right? So how do we find that? Well, Q, as before, is just equal to whatever the cross-sectional area of this little chunk of cylinder is, right? So like whatever the surface area of this boundary that's being generated as a result of this little cut, what that cross-sectional area looks like. But be aware that maybe cross-sectional area is a confusing term. Maybe we should just say, what is the surface area of the thing that we're cutting, right? So the curved surface area, like the surface area of the cylinder that is generated by creating this cut, okay? And this surface area multiplied by whatever the Q double primes are on that cut, right, on that boundary, whatever those are, assuming that they're uniform, multiplied by the surface area will give us Q. All right? So what is this surface area, first of all? Once again, it's supposed to be the surface area over which heat transfer takes place. We know that heat transfer is taking place radially outwards, all right, all along this little cut of cylinder. And so if that's the case, then the surface area that we're using is just the surface area of the cylinder generated by this cut. So let's suppose that we take that cut to happen at some arbitrary radius r, okay? What is the surface area of a cylinder, right? Well, one key thing to note, we're going to ignore the caps, all right? So if I draw a cylinder, if I draw the cylinder that we're considering, and again, this is a horrible drawing, so apologies, the heat transfer is occurring in this direction, right? Roughly speaking, it's occurring radially outwards. It is not occurring, through the caps of the cylinder. And so as a result, because we only care about the area over which heat transfer takes place, we're not going to consider the area of the end caps. We only consider the curved portion of the cylinder. And what is the curved portion of the cylinder? Well, this is basically just taking a circle and projecting it, right, down some axis. Now, be aware, right, this is not just taking the cross-sectional area of this thing and multiplying it by L. Okay, what we are going to do is we're going to take the perimeter and multiply it by L. And that perimeter, right, because the area that we want is this area right here. So what is the perimeter of a circle? it is just 2 pi r, and multiplied by whatever the length of the cylinder is. So notice that this surface area actually depends on where you take the cut. Okay, so before, the surface area of the cut that we were making didn't matter in planar systems. Like, it was always the same. Here, now it actually matters. Now we can ask ourselves, well, what is the heat flux? Well, it's pulled from the exact same expression that we had before for heat fluxes, right? So what we want is this Q double prime R. We can get it from remembering that the general expression for the heat flux vector is just the thermal conductivity times the thermal gradient, okay, times the negative. Because we only care about the radial component, all right, we therefore only care about the spatial derivative of the temperature in the r direction, all right? So we can write this down. And thankfully, because we have this information, we can write this down explicitly as a function of what the temperatures are in the system. Okay, so how do we do it? Well, we're going to add a minus k over here. What is the derivative of this expression? Well, the C2 goes away, right, because it's just a constant. The logarithm turns into a 1 over r. So we get, essentially, C1 over r, and then that C1 over r, or sorry, that C1 is this thing. All right, so we get C1 over r, which we can then rewrite using this expression, which is T1 minus T2 divided by the logarithm of R1 over R2. And then, right, that's C1, and then we have to add the 1 over R. And so this is the expression that remains. All right, this is a 1. Let me make sure that I make that clear. There we go. And so here's another interesting fact about cylindrical systems. The Q double prime is not constant in R either, right? The surface area changes with wherever you're doing the analysis. The heat flux changes as well. And so heat flux is not conserved, you know, in R in cylindrical systems, which is an interesting little fact. However, notice that the Q is, it has to be, right? Because if I have heat that's flowing from one place to the other and there's no heat that's being generated and no heat that's accumulating inside of any point of the cylinder, right? Because if not, the system wouldn't be in steady state, then of course the Q has to be conserved, all right? The Q is always conserved in systems where we make the 4 assumptions that we just talked about. And we can see that conservation occur mathematically because the R over here cancels the R over here. Okay? So this goes away, and this goes away. And so we are left with the following expression for the Qs. Now, what's an interesting fact about the Qs? Notice once again, proportional to a temperature difference, okay? So even though the equation is like nasty and nonlinear and whatever, we still get that the heat transfer rate is proportional to a temperature difference between 2 edges of the thing that we're studying, right? We also observe, right, that it's proportional to K, right? So before we had seen that we saw the proportionality to the thermal conductivity before, it shows up here again. Now that's kind of a function of the fact that the heat flux is directly proportional to K. We defined it that way, but it's still nevertheless kind of a relief to see it show up over here again. Now, we can't really say very much about the dependence on area or on the dependence on radius or length or thickness, however you want to define it, because of the fact that we have this goofy logarithmic expression, all right? It's tempting to try to say, oh yeah, it's proportional to whatever the cross-sectional area of the system is because of this 2 pi L factor, but we have to be very careful about what we mean by the surface area. I mean, it's already confusing enough to think about, like, are we thinking of the cross-sectional area of just like the circle projected, or are we thinking about the perimeter multiplied by the length? Don't think about that yet. Don't worry yourself about that yet. The only thing that matters from this perspective of doing this analysis, other than having this expression, is just the fact that we have a proportionality of Q to a difference in temperatures. That's a very interesting little fact. All right, so before we finish up talking about planar and cylindrical geometries, there's one other thing that I want to mention, which is a funny little strange fact about cylindrical systems, okay? So just like before, okay, let me see what I can erase. I'm going to erase this. So just like before, let's suppose that I have a cylindrical section. So this is T1 and this is T2. But now let's assume that I have the cylindrical section, but that inside of it, I have a full-blown cylinder, right? With some temperature T0 in the middle, right? We can say, if we want to, that, you know, there's 2 different Ks. We can come up with all kinds of goofy things for this system. We can say, you know, just like before, that this is R1, this is R2. The only thing that we have to make sure that we do is that we assume the same things we've been assuming before, right? Those 4 key assumptions of steady state, no Q dot, constant material properties, and one-dimensional heat transfer, which in this case is just radial, okay? If we make those assumptions, how can we relate T0 to T1 and T2, right? So like, what is the heat transfer in this system? And the answer is a little surprising. We can obviously find it via this analysis. So this equation is still going to be true, and this value for C1 is still going to be true, all right? But if we try to do the analysis for this cylinder over here, for the complete cylinder, right? So for the cylinder I've just added on the inside, right? It's tempting to go in and say, well, you know, the temperature at R equals 0 is equal to T0, right? It's tempting to use that as a boundary condition. But look what happens. The logarithm of 0 is not a number. The logarithm explodes at 0. And so if you try to plug in this boundary condition, what will inevitably happen is that for any value of C1 that is not 0, this expression explodes, right? The temperature of the inside of the cylinder becomes infinity or negative infinity or whatever, okay? The expression does not evaluate correctly. So, oh no, what is the only thing that we can do, right? We know, or at least we assume, that temperature should be finite. We assume that things should not be blowing up all over the place, and so a natural thing to kind of stop and say and do is to say, well, if the only value of C1 that will cause this thing not to explode, you know, if the only value of C1 that will avoid this problem is 0, then we should just use that. We should just say that C1 is equal to 0 in order to avoid the temperature blow up, all right? So if that is the case, then we have to then go ask ourselves, if this C1 is equal to 0, then what should C2 be? Well, C1 is now gone. So the logarithmic term goes away, and what we're left with is just C2, which is just a constant. So the temperature inside of the cylinder is a constant. And so this boundary condition kind of serves us both ways. It tells us, because the temperature can't blow up, right? Because this number is finite, C1 has to be 0 and C2 has to be T0, all right? So the temperature everywhere inside of a cylinder that contains its core, whenever we are assuming the 4 assumptions that we made at the beginning of this lecture, that temperature is always going to be constant everywhere inside of the cylinder. So T0 is going to be exactly the same as the temperature over here or over here or over here. It's not going to change in R. Interesting little fact. So if that's the case, right? So if the temperature on the inside of this cylinder is just T0, is there any heat transfer that's actually taking place on the inside of the cylinder? And the answer is no, right? Because remember, we said that the heat flux as a function of R is just minus K dt over dr. And there is no rate of change of the temperature with respect to R. This is just a constant. So there's no heat flux anywhere on the inside of the cylinder, and by extension, no heat transfer rate in or out. Always has to be true. So what does this mean for the temperatures T1 and T2? Right? Like, can we use this information to figure out whether or not T1 or T2, like what the relationship between them is? Notice, of course, that T1 is the temperature of the outer edge of this cylinder in the same way that it's the temperature of the inner edge of this cylindrical section. Sorry about that. And so as a result, T1 has to be exactly equal to T0. All right? So we already figured that out as well. And we can ask ourselves, is T2 different from T1? And the answer ultimately is going to be no, right? Because I can do an energy balance right here over the cylindrical section, the original cylindrical section, and I can say, well, the heat fluxes in have to balance the heat fluxes going out, right? So whatever is leaving or entering, I'm just going to, for the purpose of the drawing, assume that it's leaving. Whatever the amount of heat that's leaving the main cylinder, all of that heat that's leaving it has to also then leave the cylindrical section, right? Energy in equals energy out, or power in equals power out. But there is no energy going in because there's no heat transfer happening from the main cylinder. And so as a result, there can't be any heat transfer happening on the outer part of the cylinder. And so T2 is also equal to 0. All right? So whenever you're dealing with a problem where you assume all of the four things that we usually assume, material properties being constant, steady state, no Q dot, and one-dimensional heat transfer in a cylinder, and whenever you have the core of the cylinder in your system, you'll notice that at steady state, this has to be true. Now, obviously, there can be temperature gradients inside of cylindrical systems. I'm not trying to say that whenever you see a cylinder with its core, its temperature is going to be the same everywhere. The thing that you have to understand is that those temperature gradients have to be as a result of the fact that the cylinder hasn't reached steady state yet. It hasn't fully equilibrated. So there are temperature gradients, but then those temperature gradients over time will smooth out, right? Assuming that there's no thermal energy generation rate or anything like that, assuming that everything that we have talked about so far is true. If you observe a cylinder with temperature gradients, it means it's not in steady state, okay? Or that there's a thermal generation happening inside of it. And so this is a really cute and interesting fact about how the temperature variation of cylinders occurs that helps us understand how we can relate solutions to the heat equation, at least simplified versions of the heat equation, how we can relate those solutions to quantifiable, meaningful information about how heat transfer takes place in these sorts of systems. So now that we've taken a look at this, now the idea is to say, well, we noticed this weird thing, which is that the heat transfer rates, no matter what geometry I was using, planar or cylindrical, were always proportional to temperature differences. That's kind of interesting because in the model that we use for modeling heat transfer between two different objects, we also find that the heat transfer rate is proportional to temperature differences, right? Assuming the same assumptions. Is there something to that? Can we use that to our advantage? And the answer is yes. And we will talk about that in the next lecture.